I'm Boy Zhang from the Northwest University, and I will present our work titled From Structure to Semantics, Hypergraph-Based Augmented Reality Assembly Guidance with Large Language Model Mediated Narration. Regarding the agenda of my presentation, I will discuss the research background and the motivations, illustrate our method and user set design, describe our main result and discussion, and finally conclude the limitation and future research directions. Let's begin with the research background. Visual assembly refers to the use of computer-simulated environment to validate assembly processes and train operators for complex industrial tasks. Such systems are increasingly adopted to reduce training costs and improve operational safety. Recent literature have laid a wide foundation. Researchers have successfully used graphs for object tracking and management in augmented reality assembly. There are also extensively studies on how visual assets impacts guidance quality. However, current studies focus on tiny-scale assemblies. This is a significant lack of research addressing high-complexity assembly state. Then I would like to outline the motivation behind our work. The real-world assemblies involve hundreds of parts, and this raises two questions. First is about the structure ambiguity. Traditional Liaison graph fails to capture the procedural logic, such as subassemblies and strict consequence required here. The second is the cognitive overload. The sheer volume of visual cues overwhelms the user, causing a split attention effect between the instructions and the physical text. So we need to get deeper into how we handle this complexity of visual assembly. To address this complexity and cognitive issue identified in the previous slide, we cannot view the augmented reality system as a black box. We must deconstruct the workflow to pinpoint exactly where the guidance falls. So we organize the visual assembly system into four subsystems. First is the visual data source. Second is the post-estimation or the visual operating system. And the third is the assembly representation system, and the fourth is the user guidance system, which handle the cognition layer. By analyzing this pipeline, we identify a critical shift. While the visual tracking limited AR performance and have a high inference latency, we need to pay more attention to how we represent the knowledge and interact with the user. Therefore, we focus on redesigning the assembly representation and user guidance. Let's move on to the proposed method. We design a two-phase pipeline. The first pipeline is the assembly hypergraph. We start by transforming the physical parts into a semantically rich hypergraph. Unlike traditional graphs that only model physical links, our hypergraph can capture hierarchical structures. Then a specially designed A-star search algorithm traverses the graph to generate a machine-optimal assembly path. This leads to the second path, the large language model mediation narration. This workflow consists of three core components: an optimizer that reorders steps based on human factor principles, a retriever that queries the hypergraph for the knowledge and context, and a narrator that translates the final refined plan into an actionable augmented reality guidance. Let's take a closer look at the large language model workflow. The process begins with the optimizer shown in the orange box. Its job is to handle the logic and planning. It analyzes each sample steps, retrieves the necessary context from the graph database. Once the path is logically optimized, it passes to the narrator shown in the yellow. The narrator's role is purely about presentation and language. It takes the structured plan and translates it into a sequence of augmented reality commands. This architecture ensures that our guidance is always grounded in the facts, as shown by the assembly path schema. Next, I will describe the study design. Our study is structured around two research questions. The first question focuses on the representational level, and the second question builds on this foundation and examines the interaction level. Combining these two research questions, we want to summarize our expectations and hypotheses in the matrix. In this matrix is across three dimensions: performance, cognition, and user experience around these two research questions. To evaluate our approach, we designed a controlled within-subject user study. We recruit 24 participants with engineering background. Their task was to assemble this complex 25-part robotic gripper. And each participant experienced all three guidance conditions and the order was counterbalanced using a Latin square design to mitigate learning and fatigue effects. A crucial point is that we use a Wizard of Oz methodology to ensure the experiment's internal validity. Now let's look at what the participants actually saw. Here are the three conditions they experienced. First is the reaction graph baseline. This represents the standard approach. The system provides a simple linear sequence of instructions showing only the immediate next connections. There is no higher level structural context. Second is the hypergraph condition. Here, the guidance is structured and stage aware. The system groups related steps into sub-assemblies and enforces pre-execute checks. However, it presents the raw structure information without any genomic optimization. Finally, our full system, the large language model and hypergraph condition. This condition uses our large language model mediation workflow. It translates the raw hypergraph structure into an economically optimized and coherent narrative. Now I'll present the main results. But before presenting the specific outcomes, a crucial concern in the within subject study is the potential of order effects. We conduct a separate analysis treating the presentational order as the independent variable. As shown in the section, we found no significant mean effects across the main matrix. Interestingly, where users learn the text over time, the physical fake from the prolonged AR usage caused test time to increase. So this confirms that our Latin square design successfully balanced these opposing factors. At the result. First part is the objective results. Regarding the performance, while general tasks showed marginal gains, the large language model method showed a significant reduction in the assembly failures. The narration clarified how to perform steps. And second, in the attentional dwell time, we saw a massive effect participants using the large language model method spent significantly less time verifying the animated model. Most importantly, the hypergraph caused the cognitive cost of processing new raw structure. However, the large language model narration successfully mitigated this, smoothing the workflow back to the baseline levels. Moving to the subjective results, the data reveals distinct role of structure and narration. For usability, we observe a clear stepwise improvement. For the workload, the NASA Task Load Index and the Technology Acceptance Model, the results show that the hypergraph structure was the main driver. The large language model's unique contribution shines in the immersion. Our analysis of confidence intervals shows that the hypergraph made the task interesting, and only the large language model-mediated narration significantly improved the flow, focus, and attention. Next, we will briefly discuss the implications of these findings. Our findings suggest a progressive enhancement, which the two components played in distinct but complementary roles. First, the primary contribution of hypergraph is the representational capacity. We confirmed that the hypergraph provides clear benefits. We also identified the trade-off. Users had to switch to their attentional more frequently to map the abstract structure to the real world, which supports the hypothesis 1.3. This led to the economic mediation. Its primary benefit was attentional optimization. It counterbalanced the switching costs, smoothed the workflow back to the baseline level, which supports the hypothesis 2.1. Furthermore, it offers a critical refinement. It shifts the user from watching animation to engaging with text instructions, which supports the hypothesis 2.2. Finally, we acknowledge the limitations of our current study and outline our future work. First is about the demographics. Our participants are mainly consist of students. And the second is the system implementations. The current large language model narration is an offline optimizer validated by Wizard of Oz operators. And the third part is the scalability scope. We only validate on the single rigid body assembly task, although it's quite complex. And the hypergraph and the algorithm struggle with continuous operations like wiring and fluid methods. And then let's come to the future work. First, we plan validation in real-world settings. And second, we will develop a real-time adaptive system. Finally, we envision a geometry-centric evolution, which are hoping to solve the system of the non-rigid tasks we mentioned above. If you are interested in our research, please do not hesitate to contact us. Thanks for your attention.